Slew rate for an op amp is a measure of how fast the output can change. If you remember, all electronic circuits have some kind of propagation delay. Transistors can't switch instantly. Switching speeds for electronic circuits are very fast, many times so fast that we don't even think about worrying about it. But other times, we may run into a limit where we do have to consider what is the fastest that circuitry can actually carry out a task. In digital circuits, you run into that, of course. With op amps, you'll see that different op amps have different speeds that they can keep up with. And it's maybe one of two uh, characteristics that manufacturers will advertise for their op amps. I mean, there's other ones too, but if you're going to brag about your op amp, it's going to be slew rate. If it's a fast op amp, you'd have bragging rights if it can keep up with a signal that's traveling or changing fast, which turns out to be frequency a lot of times for us. And gain bandwidth is another characteristic that a manufacturer would post as a way to advertise their op amps characteristics and if it's better than another one. We will look at slew rate and gain bandwidth. We'll do slew rate in this video, and then I'll do another video for gain bandwidth. If an op amp has a high slew rate and if an op amp has a high gain bandwidth, those are good things, and you will pay more for an op amp that has high numbers for both of those. I think the 358, I forget what we paid for that, 20 cents or less. So it won't be super high numbers there. And it's I suspect its intent is oftentimes to be used with DC, which, by the way, op amps, the amplifier we made, and we put a sine wave through it, but it works equally well with DC. You can direct couple, and you can bring DC signals in, and it'll amplify those. Same magnitude of amplification. If you applied a tenth of a volt to a gain of 10, you'd get a volt out. But you will pay more for an op amp with high slew rate and high gain bandwidth. I remember a student telling me a story. I think it was maybe Marshall amps that an engineer insisted that they use a certain op amp that he wanted for the design, and cost $50 for that op amp. So it's quite a wide price range, huh? From 20 cents or maybe a little less. You could pay as much as 50. I don't know where they're at nowadays. If there's still op amps at that high of a price, I don't know. So we said slew rate is a measure of how fast the output of the op amp can change. So what do we mean by that? Well, we could take a simple voltage follower layout. That makes it easy. And if your input is changing from 0 to 1 volt in a certain amount of time, can the output do the same? It's as simple as that. And that certain amount of time can be explored. So we'll look at how to do that. The easiest way to see the limits of how fast the output can change is not to put varying frequencies in and watch for distortion. I mean, that's another thing we can probably experiment with. But probably the simplest is to hit it with a square wave, which essentially asks the output to change instantly. And it won't be able to, but you'll be able to see it do its best. And that slope will show you exactly the slew rate. So let me show you what I mean. So if we apply a square wave to the input of our voltage follower, we're essentially asking the op amp to change from here to here, here to here, instantly. And it can't, but it's going to do the best it can. So let's see what that looks like, and it'll reveal the slew rate instantly. If the circuitry inside the op amp here had infinite speed, it could track and move from here to here instantly. It does have it has a finite speed, of course, not infinite. So it will get from here to here as fast as it can. And that might look something like this. The slew rate is simply the slope of this line that would show up on your scope. Of course, you have to sweep your scope fast enough to maybe stretch this out to make it easy to measure. But that's all there is to measuring the slew rate. Just um, use a square wave. It makes it easy. Picking the frequency of the square wave, any frequency will work. But of course, you want to stretch out your time base on your scope so that you get an easy slope to look at and to measure. So you're going to want to have a rather fast time base for your scope, sweep fast, which means you probably want a higher frequency square wave also. It's just all about stretching things out to make it easy to measure. So the slew rate is then the change in voltage over the change in time. If you were to look here, it'd be maybe this voltage changed from here to here, and it happened in this amount of time from here to here. And that would give you a number for the slew rate. Oftentimes, the slew rate is noted on data sheets, typically in volts per microsecond. I mean, volts per second would be a high number, you know. So, I mean, maybe the speed that the output can move, if it was in seconds, it could be like 1,000,000 volts. It can travel that far in a second. That's nice. I'm not using 1,000,000 volts in my circuit. So lots more frequently, it's specified in microseconds. When you use a square wave to ask the op amp to change instantly, you'll reveal how fast it can change. You'll also reveal some other things. Square waves are one of the toughest things for electronic circuits. I guess no surprise, right? You're asking things to change instantly, they can't, and things happen. You're also dealing with things like magnetic fields and things like that that are changing very rapidly. So, oops, didn't mean to do that. Clicked the wrong button. So you'll see things like what's called settling time. I mean, it'll go as fast as it can trying to get there, and then it has to slam on the brakes. So, I mean, there might be a little ringing and settling time. And then when it gets told to go, it gets slammed in the other direction, you know, little magnetic fields collapsing, you know, a little spike, who knows. But yeah, you'll see all these things. Settling time's a big deal too. You know, this ringing, you know, will show up, and just little anomalies and stuff, which also brings up another point. When you're trying to measure slew rate, um, you know, stay away from the messy parts, you know, um, because it's going to be a little messy. Anytime you hit a circuit with a square wave, things get a little messy under magnification. I mean, this is going to be, your scope's going to be scanning rapidly enough to pick up a slope line that you can measure to get the slew rate. And at that fast scanning rate, it'll show you all the little details that sometimes you don't care about, sometimes you ignore, although you might need to pay attention to them. Uh, but these are the little anomalies that show up under this higher magnification. So they'll be there, but for us, when we want to try to measure slew rate, you want to just stay away from those parts where it's settling down and stuff. Yeah, so here you can see the idea. Um, we're trying to measure the slope of how fast the output can actually change. And we're going to pick a nice clean section here where there's no ringing or other spikes or noise. So, you know, here's a nice clean section from here to here. So there would be my change in time and my change in voltage. Of course, rise over the run. So it is a slope, and it's just a speed is what it is. It's how fast the output can change. Here you can see a capture that I did with the analog discovery. It's a voltage follower. It's the 358. I have it powered up +5, -5. I got a 100K load on it. So both channels on the scope are 1 volt per division. You can see that. And I'm inputting a square wave that goes from, looks like -3 volts to +3 volts. Be careful not to exceed the compliance of the amp. That'll show other distortion and get confusing. So I have my 3 volt peak signal. I picked 50 kilohertz just experimentally. If you have an op amp that you're not familiar with, you just start somewhere. I mean, give it a square wave, make sure you're within its compliance, um, and then you're going to just maybe increase the frequency until you have things stretched out as much as you want. So I have it stretched out with a time base, 5 microseconds per division, and it gives a nice picture, I think. You can see that ringing, settling, some little spikiness here, and then off you go. And this is the speed that the output can change. That's the fastest it can change. I mean, you're not always asking it to change that fast. If you have a slow frequency, a lower frequency, a sine wave, for example, doesn't change on a dime. So, but this is at the fastest the output can change, and that's known as the slew rate. Like we said, here's the ringing again. Here's my measurement of the slew rate. I just used vertical cursors, and you can see I just used the grid lines to line up with. I just grabbed the point that was at -2 volts, and then the change in voltage is to +2 volts. So there's a change of voltage of 4 volts that occurs from this time to this time is the amount of time it takes from here to here to get from -2 to +2, right? So I have a change of 4 volts that occurs in this amount of time, and I can do the math, and I can get my speed that the output of the 358 is capable of changing at, otherwise known as the slew rate. You can see why slew rate is given in data sheets as volts per microsecond. That's usually the around where you're at. I mean, here I have a change in microseconds and I've got 4 volts change for a certain amount of microseconds. So I could just do the math on that, but it'll be volts per microsecond. So let's pick an example number for slew rate. Let's say we have an op amp and it can change. It has a speed maybe half a volt per microsecond. That's how fast the output can change. You can use this slew rate to tell you the maximum frequency that the op amp can handle for a sine wave. So let's do that. If you look at the sine wave, you can see we're not asking the output to change instantly as we were with the square wave, but there still will be a frequency of sine wave that could be traveling faster than the output could keep up with. And that would be seen if you had a sine wave input and output, and then the output started to have trouble keeping up. It would start to separate a little bit. The sine wave's moving at this speed at that rate, and your op amp, if it couldn't keep up anymore, you would start to see some separation here. It would almost look like phase distortion, but it would start to separate. Also, it wouldn't make it to the peak, in time. So the peak would start to reverse, so you would see it sort of as attenuation. I'm not sure if that's an exact sketch. I'd have to revisit what that looks like. But we can do that with our analog discovery and see what slew rate distortion with a sine wave input and output looks like. It does indicate that you've gone past the op amp's ability to keep up. It's not as apparent of a way as a square wave. A square wave reveals the fastest it can do. The sine wave would be a little tougher to measure slew rate. However, you can see when the output's not a faithful reproduction of the input, a slew rate distortion happening, that you've exceeded the maximum frequency. So we'll get back to how do we calculate that. That's what we'll do next. So we can investigate what the actual slew rate distortion looks like with our analog discovery when you've gotten a sine wave with a frequency that's higher than the op amp can keep up with. What I want to show you next, though, is the way you would calculate the maximum sine wave frequency that an op amp can handle based on its slew rate. And that's this formula, fairly simple. You just take the slew rate and divide it by 2 pi times the voltage peak. The voltage peak is important to remember. It's not peak to peak. It's how far you're asking the output to travel in either direction. So I mean, if you think about it, it never it's how much you're asking, how far you're asking it to go from here to here is really what you're using in the formula. So this formula tells you the maximum sine wave frequency that this op amp can handle. A couple things, of course, like we said, make sure you remember to use the peak voltage in the formula. Make sure also that you remember the slew rate comes with uh, it comes in the form of a fraction. So don't ignore don't ignore the microseconds here. In other words, that's a common mistake I see students do, but it's 0.5 volts per microsecond. So you have a fraction over a fraction here. So watch out for that. So I think you can handle that. But there's your two pitfalls that I usually see students make. They forget about the microseconds. They just put 0.5 in the numerator. That'll get you things wrong in a hurry. Um, or they forget to use the peak voltage output. Maybe they use peak to peak. But use peak. Don't forget about your fraction. And actually, I'm remembering why we use V peak here. Um, we can break this formula down into a very familiar formula. Uh, Frequency, we could rewrite that as the inverse of the period, 1 over t. Scoot that over a little bit so I have a little more room here. Slew rate, that's the speed of the op amp. Okay. And then this 2 pi v peak is actually distance. Think back to a sine wave being the y values as you rotate through a Cartesian plane. V peak is also the radius, if you remember, and there are 2 pi radians in 1 revolution. So in 1 revolution, which is also 1 cycle, there are 2 pi radians, and each radian is an arc length of the peak voltage. So it's really telling you here how far in volts you're asking the output to travel. This is the distance in volts that you travel for each cycle time. So here's your distance that you have to go, 2 pi v peak. That's how many volts, that's the distance in volts that you have to travel in this much time, right? Because that's the cycle time. And one cycle or 1 revolution contains 2 pi radians, and a radian is equal to an arc length equal to the radius. Well, that radius is the peak voltage. So that's why we're using peak voltage. So it breaks down to that familiar formula that you used a long time ago, for the first time, maybe in a math class, perhaps. But let's see if we can reshuffle things here. We can bring distance over to this side, right? And we have distance that you go. I brought distance over. This is inverse. I'm going to take time over to this. You're already ahead of me. I'm sure you see this, right? So it's speed times time equals distance. So bottom line, this formula you can use, and it will tell you the maximum frequency that a given op amp with a given slew rate. It'll tell you the maximum frequency that that op amp can keep up with. Keep in mind another very important factor is the peak voltage that you're asking it to get to on the output. So it's how fast the op amp can move, how what is the speed that it's capable of for that particular op amp. But it's not just that. It's how far are you asking it to go, and then how much time are you giving it to get there. So, um, uh, for example, if you had an op amp and you weren't happy with the frequency that you could use, you hit slew rate distortion before you got to the frequency that you needed it to be able to handle. You might be able to remedy that just by lowering the peak voltage that you're demanding from the output. Um, so they all play together. So they're trade-offs. I mean, if you want it to be able to go, if you want a high amplitude output, you're going to have to sacrifice frequency for that. It won't be able to go to as high of a frequency before you hit slew rate distortion. So they are trade-offs of each other. Um, if you want high frequencies and high amplitudes, you're going to need an op amp with a high slew rate for sure. And otherwise, you can maybe compromise one for the other. You can maybe back off the peak voltage that you're asking it to get to. It won't have to go as far. Um, or you could back off the frequency that you're asking. So, but you can see the speed, time, and distance relationship right here. This one you can't change. This is from the manufacturer, so that's how fast the op amp can move. That's how fast it can go for the output. So you're stuck with that, or buy a new op amp, buy a different op amp with a higher slew rate. But for a given slew rate, you can play with these two factors. They're trade-offs of each other. So you could, um, maybe require less peak voltage and get a higher frequency capability, or you could back off the frequency and get a higher peak output capability. And there I put 1/time if that was bugging you, but that's what the frequency would be equal to. But it's in our mind, it's all about the time. But yes, it's 1/time there, speed here, distance here. If that whole speed, time, distance thing isn't working for you, or if that just it didn't really follow well for you, it's okay. Just still hold on to the formula itself, and just know that you've got these elements to play with. The op amp speed, and of course, you can sacrifice peak output to get higher frequency capability, and vice versa. Last thing, just to finish up, I guess we could do a quick example. We could of the math. Um, we could use that zero point 0.5 volts per microsecond. Um, I don't know. Let's pick something here. Let's just say we had a 1 volt peak, and let's see what kind of frequency, how high of a frequency can we go before the op amp couldn't keep up. So let's do that. So here it is. Again, don't forget you've got a fraction here for slew rate. Do not put zero point 0.5 in for slew rate. It's zero point 0.5 per microsecond. So that number, you can see where your mistake would be. It's actually 500,000. I wrote it out so you could really see and hopefully not forget. That is the classic mistake. I see students most often they just put 0.5 in for the numerator because that's the slew rate, 0.5, but it's 0.5 per microsecond. So you got your 500,000 written out for you as a reminder, and then 2 pi, well, it's just 1 volt peak, so that was easy. And then finish it off. And what the formula is telling us is that this op amp with a 1 volt peak output signal, it can handle a sine wave frequency of 79.6 kilohertz. I rounded for that. And if you go higher than that, you can expect it to have some slew rate distortion where the output can't keep up with it. And the higher frequency you go, the worse the slew rate distortion would become. I'm thinking I remember if you push it really far, you'll see the output looking like a triangle wave, I think. If I think. Try it. We can try it with our analog discovery. Um, you can have a sine wave input, and if you've got a triangle wave looking output, yeah, that might be an easy indicator. I don't totally remember, so we can experiment with that, see. But I do remember triangle wave showing up somewhere. That could have been just with a square wave, but it might happen with a sine wave of high enough frequency. I don't remember. So those are things we can experiment with. We can check it out, but those concepts should set the stage. Last thing I think, unless I think of something else, but uh, quickly I wanted to show you there's your 1 volt peak output. If I needed 2 volts peak, this goes right in half. It's just that easy. The formula is not complicated. So if I did need a 2 volt peak, now I can only go as high as 40 kilohertz. And conversely, if I was able to get away with just a half a volt peak, I would have maybe twice the frequency capability. So half a volt peak, and I could go to 160 kilohertz approximately. Okay, we'll have some fun experimenting and measuring.